Welcome back. We are now on lesson 2 of chapter 10. So if we remember back in section 1, we learned how to graph our radical functions. So now what we're going to do is we're going to take our radical expressions and we are going to simplify those. So if we remember correctly, a radical expression is something that looks like this, something like the square root of 80. So what we have to do is we can't leave the square root of 80 as the square root of 80. We also can't just plug it into the calculator and get a decimal approximate for it. If I ask you to simplify it, we have to actually simplify the radical. So when we simplify our radical, we have a couple of different rules that we have to follow here. The first rule is that no radicands have perfect square factors other than 1. So what that means, if we remember correctly, a radicand is the number that's underneath the radical. So in this case, it would be 80. So seeing as that's the rule, 80 would have to have no other perfect square factor other than 1. But it does. 80 has a perfect square factor of 4. Now we'll talk about our perfect square factors in a second, but we have to understand that if it does, that means that we can simplify it. So if underneath the square root it was something like the square root of 13, that can't be simplified because that doesn't have any other perfect square factors other than 1. So that's the first rule. The second rule we have to follow is no radicands contain fractions. And this is something that we have talked about previously when we were talking about our radicals before. We can't have a fraction as the radicand. And we do know how to work with that, but we'll talk about that again in a little bit. The third rule that we have to follow is no radicals appear in the denominator of a fraction. So again, what that means, sorry, I can't spell, is that we can't, when we're working with fractions, we can't just have a radical in the denominator. So again, we have to find some way that we can simplify that. Now, in order to do all of this, we have to work with what we call the product property of square roots. And all that that shows us is that if I have a radical, something like the square root of a times b, what I can do is I can actually rewrite that and split it up and put it as the square root of a times the square root of b. So whenever I have two numbers being multiplied underneath a radical, I can split them up and put them separately in their own radicals. And that also goes the opposite way too. If I have two radicals here that are separate but being multiplied together, I can multiply them together under a single radical. So something like, for example, if I had the square root of 4 times 9, I can take this and I can just rewrite this as the square root of 4 times the square root of 9. And now I can say, well, I know what the square root of 4 is. The square root of 4 is 2 because that's a perfect square. The square root of 9, that's 3 because, again, that is a perfect square. And now that is going to simplify to just be 6. So that's what we mean by simplifying a radical. Just because it's under a radical doesn't mean that it can't be simplified. So now let's look at the square root of 80, and let's actually try and simplify that. So like I said before, we need to understand what our perfect square factors are. Well, if we remember our perfect square factors, we have 1, but we want other than 1, so we really aren't going to use that, but we'll keep it there. Then we have 4, then we have 9, 16, 25, 36, 49, 64, 81, 100, 121, 144, 169, 196. And then after that, we really don't need to know too much more. We should know all of these perfect squares, because again, all this is this is 1 squared. This is 2 squared. This is 3 squared, 4 squared, so on and so forth throughout the entire thing. So these are our perfect squares that we should know. So now what we have to do if we're looking to simplify the square root of 80, we have to say, okay, which one of these is going to be the greatest perfect square that is a factor of 80? So what we could do is we could just go and divide all of these by 80 and see which one works and which one is the greatest one. Which for some of you that may have to be what we do. My suggestion is we see that the number is 80, go to where 80 would be, which would be right here, and we know that our perfect square factor has to be one of these numbers. So if we're really not sure, again, we got our trusty calculator, we take 80, we start dividing by 64. And if you get a whole number, then that's the one we're going to use. If not, then we move on to the next one. So now if we do 80 divided by 64, we don't get a whole number. We get 1.25. So that's not the one that we're going to work with. So then we move on to 49. 80 divided by 49, that's going to give us 1.6. Again, that's not the one we're working with. So 80 divided by 36. 80 divided by 36. That's going to give us 2.2, so that doesn't work. Then we want to do 80 divided by 25. And that's going to be 3.2. That doesn't work. So we're seeing that we're getting rid of a lot of our perfect square factors here. 80 divided by 16. And now if I see that, 80 divided by 16 gives me 5. So this is the number I'm going to want to work with. So what I can do now is I can take 80 and I can split 80 up into two different factors, 16 and 5, because 16 times 5 is 80, and 16 is the greatest perfect square factor. So now I have the square root of 16 times 5, and if I go based on what we did here, I can just take this and rewrite it as the square root of 16 times the square root of 5. But we know that the square root of 16, that's going to be 4. So now we are just left with 4 square root of 5. That is going to be my final answer. That is how we simplify a radical. We have to split it up into its greatest perfect square and whatever the other factor is, split those two up, and then take the square root of the perfect square that we got. Alright, so let's try one more, maybe two more of these, just to make sure that we understand what's going on here. So let's say we wanted to take the square root of 54 and simplify that. So again, you may want to have your list of perfect squares on the side here. So 1, 4, 9, and we just have all of these on the side. And I'll just stop there for this one. So I know that the number 54 obviously is going to fall somewhere right here. So that means I should check every number above 49 to see which one of these is going to be the greatest perfect square. So again, over to the calculator, I do 54 divided by 49. That gives me a decimal, so that's out of the question. Then I do 54 divided by 36. That's 1.5, so out of the question. 54 divided by 25, 2.16, that's no. 54 divided by 16, that's 3.37. Then I do 54 divided by 9, that's going to be 6, so that one works. So that means that I can rewrite the square root of 54 as the square root of 9 times 6. Which then means that I can take that and rewrite this as the square root of 9 times the square root of 6. And the square root of 9, seeing as that's the perfect square, that's going to be 3. And then this just stays as the square root of 6. So my answer would be 3 square root of 6. Now let's do one more. Let's say we had the square root of 180. Okay, so we're actually going to have to expand our list a little bit here. So we got 100, then we got 121, 144, 169, 196, and then we can stop there. So I'll use a different color for this side here. So 180 is going to fall somewhere here. So that means I have to try every number below 180. Again, this may take a little time, but this is going to be the best method to be getting this highest or this greatest perfect square factor. So again, over to the calculator, 180 divided by 169, that's 1 point something, so that doesn't work. 180 divided by 144, 1.25, so that's a no. 180 divided by 121, still no. 180 divided by 100, we should probably know that that's definitely a no. But 180 divided by 81, still no. 180 divided by 64, still no. 180 divided by 49, still no. 180 divided by 36, that is going to be 5. So I now come back over to my 180. I rewrite this as 36 times 5, the square root of. And again, I take that, I split it up into the square root of 36 times the square root of 5. I know that the square root of 36 is going to simplify to be 6. So I end up with 6 square root of 5 as my final answer. So now we're going to move on to a little bit more complicated ones. Let's say instead of just having a single radical, something like we had before, like the square root of 80, let's say now I want to simplify something like the square root of 2 times the square root of 14. So I do not have a single radical now. Now I have two radicals multiplied together. Well, that shouldn't be too much of an issue because we know from our previous method that we can take this and we can just rewrite this as the square root of 2 times 14. We can put these together into a single radical. Well, now we just have to figure out what 2 times 14 is, and again, that's just a simple calculator problem. 2 times 14 should give us 28. So I now have the square root of 28. And now I can just go back to what we were doing before with our perfect squares. And trying to figure out which one is my greatest perfect square. 28 divided by 25, not a whole number. 28 divided by 16, no. 28 divided by 9, no. But 28 divided by 4, that's going to give me 7. So I can rewrite this as 4 times 7 under the radical, which can rewrite as square root of 4 times square root of 7. Square root of 4 is 2. So I have 2 radical 7. If we do something again, it's another problem like this. Let's say we had something like, let's go with the square root of 6 times the square root of 8. Same concept. We take the two numbers, we're going to multiply them together first. So 6 times 8, we have the square root of 6 times 8, which is then 6 times 8 just gives us 48. So I go back to my list of perfect squares. And I'm working with any number that is less than 48. So I'm working with every number from here and down. So I start with 36. 48 divided by 36, no. 48 divided by 25, that's going to be a no. But 48 divided by 16, that's going to give us 3. So we rewrite the square root of 48 as the square root of 16 times 3, which we can then rewrite as the square root of 16 times the square root of 3. And the square root of 16 gives us 4. So my final answer would be 4 square root of 4 square root of 3. So now that we know how to simplify a square root with just numbers, now we want to take it and try to simplify a square root with not only numbers, but numbers and variables. So now we're going to look at something like the square root of 90, x to the third, y to the fourth, z to the fifth. So now we want to look to simplify something like this. Well, this isn't really a problem because, again, if we go based on our product rule, we can take this and just rewrite this as the square root of 90 times the square root of x to the third times the square root of y to the fourth times the square root of z to the fifth. And now we can work with each of these separately. We know how to do the square root of 90. We just talked about that before. Work with our perfect squares. Work with everything above or below 81 in this case. Which one of these is going to be the highest perfect square of 90? And if we work with that, we know that 81, 64, 49, 36, and 25, and 16 all don't work, but 9 does. So the square root of 90 gets split up into the square root of 9 times 10. The square root of 9, this then splits up into the square root of 9 times the square root of 10, and the square root of 9 becomes 3 square root of 10. So that's good for the square root of 90. But now I've got to work with the variables. Well, the rule with variables is this. You're going to take your exponent. Whatever your exponent is, you're going to divide that by 2. Now, if you remember back to like elementary school when you did long division, right? If I wanted to take 3 and divide it by 2, I would do something like this, and I would say, how many times does 2 go into 3? Well, that would be 1. And then we always worked with this remainder, right? Well, in this case, we would have a remainder of 1. So what this means in terms of this, whatever this number out here is, this is going to be the exponent of what is on the outside of the radical. So in this case, we have the square root of x to the third. So on the outside of the radical, I'm going to put x to the first power because of this number right here. That's going to go on the outside of the radical. The remainder, that is going to be the exponent of whatever is inside the radical. So I'm going to have an x to the first on the inside of the radical as well. So the square root of x to the third actually becomes x square root of x. Now I'm going to do the same with the rest of these as well. So I'm going to come over here to the 4, and I'm going to say, okay, I have an exponent of 4. So that means I'm going to take 4. I'm going to take 2 and divide 4. How many times does 2 go into 4? 2. Well, this doesn't have a remainder. This has a remainder of 0. If I don't have a remainder, that just means nothing is left underneath the radical. Everything is outside the radical. So this is going to end up being y to the second power on the outside of a radical. I'm not going to do the same thing with z. I have z to the fifth power. So I'm going to take 5 divided by 2. 2 goes into 5 2 times with a remainder of 1. So that means on the outside of the radical, I'm going to have a z to the second power. Inside the radical, I'm going to have a z to the first power. Now with this, now that I have the final part of each of these parts, I have to put them all together now. I can't just leave them separate. So in order to put these together, what I want to do is anything that is outside of a radical is going to go out front. You always start with the number. So the 3 is going to go first, then the x to the first, then the y squared, then the z squared. That all goes out front. Then, whatever is inside of the radical, I'm going to put underneath a single radical. Again, always start with the number. 10, x to the first, there is nothing in the y, z. So my final answer would be 3xy squared, z squared, square root of 10xz. So let's do another one of those because that may have been a little bit confusing for you. So let's try something like the square root of 32 r squared k to the 4th t to the 5th. So let's work with this one. So with this one here, what we want to do is, again, split this up. Square root of 32 first, square root of r squared, square root of k to the 4th, and square root of t to the 5th. We're going to work with each of these separately. Okay, so starting with the 32, we're going to take this and we're going to look at our perfect squares again. And again, you should just have this on the side of your paper almost at all times when looking to simplify radicals. You should just have all of your perfect squares written on the side here. So we have 1, we have 4, 9, 16, 25, 36. Now that's all I have to go to for here because 32 is going to fall right here. So I check everything on this side of the 32. So in this case, 25 doesn't work, but 16 does. So 32 is going to split up into the square root of 16 times 2, which then becomes the square root of 16 times the square root of 2, and the square root of 16 is 4 square root of 2. So the number 1, done. Now we move on to the variables. R squared. So for the r squared, I take the exponent and I divide it by 2. So when I divide it by 2, I get 1 with no remainder. So this is now going to end up being r to the first on the outside of the radical. Then I move over to the k. I take the 4. I take 2 divided by 4. And I get a 2, again with no remainder. So because we have a 2 here and no remainder, again, nothing goes on the inside of the radical. We only put it on the outside. So we're going to have k to the 2nd power on the outside of the radical. Do the same thing with t. We have t to the 5th. So I take it, take 5 divided by 2. I get 2, but this time I have a remainder of 1. So here, I'm going to have t to the 2nd, because of the 2 here, on the outside of the radical, and a t to the 1st on the inside of the radical. So now that I've finished all of these, I'm going to go and I'm going to put anything that was on the outside. So I'm going to start with the number here, the 4. Now, with this r, and I do have to actually explain something I forgot to explain in the last problem. Whenever your original exponent was even, and the exponent on the outside of the radical now becomes odd, which in this case it is, we have an even exponent here of 2, and an odd exponent here of 1, this here actually has to be put within absolute value signs. Okay? That only goes for going from an even exponent to an odd exponent on the outside of the radical. We don't worry about it inside of the radical. That'll never be an issue. But if I have an even exponent here and it becomes an odd exponent on the outside, we have to put absolute value bars around that specific radical, or sorry, that specific variable. Okay, here we don't have to do it. Yes, 4 is even, but it becomes an even exponent on the outside of 2. So we don't have to worry about it here, and here we don't have to worry about it because this isn't an even exponent. This is odd. All right, but do you see how the difference is when we have an even exponent going to an odd or an even exponent going to an even? So this one here does not have to be put within the absolute value bars. We can just put that normally. Same with this t squared. We don't have to put absolute value bars around it. So this is what we're going to have on the outside, but then we also have to remember we have to put what's inside it as well. Always start with the numbers. 2, nothing on the inside here, nothing on the inside here, and a t to the first on the inside here. So my final answer would be 4 absolute value of r, k squared, t squared, square root of 2t. So the next thing we're going to talk about here with simplifying our radicals is what happens if I get the radical of a fraction. Something like if I had the square root of 35 over 15. Well, if we remember back to what we had said previously, we can't have a radicand that is a fraction. So this actually cannot stay as it is. But based on what we know from previous, we can take the square root of a fraction and we can rewrite it as the square root of the numerator over the square root of the denominator. So this is fine. But now the problem is this goes against Rule 3, which says we can't have a denominator that has a radical with it. So now I have to go with this. I have to figure out what am I supposed to do here. So really, the first thing that I should do, and I shouldn't have even started by doing this, the first thing I should always do is look at the fraction that's underneath and see if maybe this can be simplified. So if I look at 35 over 15, I do see that this can be simplified if I divide, both of these by 5. So this 35 over 15 actually would become the square root of 7 over 3. We do still end up with the same issue though. We have the square root of 7 over the square root of 3. So I do still end up with this same issue of having a denominator that has a radical in it. So the way that we get rid of a denominator that has a radical in it is we rationalize our denominator. Okay, rationalize the denominator. So what that means in order to rationalize the denominator is if I ever have a denominator that has a radical in it, something like this. So if I have, I'm going to put it in every term here. If I have the square root of a over the square root of b, in order to rationalize the denominator, all I have to do is multiply this entire fraction by whatever the denominator is. So in this case, I'm going to multiply it by the square root of b over the square root of b. Now, remember, I can do this because this is essentially just multiplying by 1. Square root of b over square root of b, this is just 1. So I'm not changing the value of the number, I'm just changing what the number looks like. Okay? So all I would do here is if I did the top part here, square root of a times the square root of b, we know that that's going to be the square root of AB, because this is what we talked about previously. On the bottom, though, the square root of b times the square root of b, if we think about that, that's going to be the square root of b times b, which is the square root of b squared. But again, a square root and a square, those are going to cancel each other out, and we're going to just be left with b, no square root anymore. So now we don't have a square root in the denominator, so it follows that third rule. So this is how we rationalize our denominator. So if I go back to the problem here, square root of 7 over the square root of 3, in order to figure this out, in order to simplify this, I would take this and I would multiply it by the denominator, square root of 3 over the square root of 3. So I would start with the numerator here, square root of 7 times square root of 3. That's going to be the square root of 7 times 3. On the denominator here, square root of 3 times square root of 3. That's going to be the square root of 3 times 3. 7 times 3 is 21. 3 times 3 is 9. But now we see the square root of 9, that's a perfect square, so that is going to end up being 3. And as we see, now my denominator is rationalized. We don't have a square root in the denominator. Now in this case, the numerator does not have to be simplified, but if we had to simplify the numerator, we would need to simplify it. Now I know that this doesn't work because if I did my perfect squares and I tested them all, there's nothing that works, so it would just stay as the square root of 21. But this would be my final answer. So let's try another one of those just again to make sure that we understand what's going on here. So let's say we had the square root of 6y over 12. Okay, so again, using the fraction under a square root, we take the square root of the numerator, 6y, over the square root of the denominator, 12. Well, again, here we need to rationalize the denominator because we have a radical in it. So all that means is I'm going to multiply the top and the bottom by whatever the denominator is. So in this case, the square root of 12. So I'm going to multiply the top by the square root of 12. 6y times 12, that's going to give us 12 times 6 is going to give us 72 y over square root of 12 times square root of 12. That's going to be the square root of 144. But we know that 144 is a perfect square. That's going to be 12. Now I do have to focus on the top here, 72y. This needs to be simplified. So I have to take the square root of 72y and simplify this. So this becomes the square root of 72 times the square root of y. So again, I go to my trusty perfect squares over here. Oh. Sorry about that. I was a little ahead of myself. Alright, we can stop there. So 72 falls right here. So I'm checking all of the numbers above it. So again, start with the 64. 72 divided by 64, that's a no-go. 72 divided by 49, that's a no-go. 74 divided by 36, still no. Oh wait, why am I doing 74? 72, sorry. 72 divided by 36, that is a go. That's going to be 2. So here, this is going to, over here. This is going to split up into the square root of 36 and 2, which again is the square root of 36 times the square root of 2. And the square root of 36 is 6 square root of 2. Now the square root of y, if I were to take the exponent and divide it by 2, I would get 0 remainder 2. So this, or sorry, 0 remainder 1. This is just going to stay as the square root of y. There is no simplification that can happen there. So this ends up becoming 6 square root of 2y. So this is the numerator. So this is what's going to go in place of that. So this now becomes 6 square root of 2y over 12. But the last thing we have to check is we have to check if there's anything else that can simplify. And what I see here is 6 over 12, that can be simplified, right? We can take the 6 and the 12 and we can divide both of those by 6, which is then going to make this just become a 1, so I can just rewrite it as square root of 2y. I don't need to put the 1 in front. And then 6 divided by 12 gives us 2. So my final answer would be square root of 2y over 2. Now please know, you cannot simplify something that's underneath a radical with something that's not underneath a radical, which is why I can't take this 2 and divide those by 2. It's why I could take this 6 and 12 and divide them. Okay? You cannot take something underneath and divide it by something that's not underneath. So now last thing that we need to talk about here is still rationalizing a denominator, but what happens when I have something like this, 3 over 5 plus the square root of 2. So here, again, unfortunately it doesn't follow our third rule, which is you can't have a radical in the denominator. But now, if I just go by what we've been talking about and taking the whole fraction and just multiplying the top and the bottom by the square root of 2, let's see if that's going to work here. So when I multiply both the top and bottom by square root of 2, the top is going to become 3 square root of 2. The bottom here, because this is a binomial, this is actually going to have to get distributed to both of these terms. So this is going to be 5 times the square root of 2, and this is going to be square root of 2 times square root of 2, which that's just going to become 2. But unfortunately, I haven't fixed my issue. I still have a denominator that has a rational in it, that has a radical here. So this does not work. I can't do it this way. I have to find a different way to multiply or to simplify when we have something like this, when I have an addition or subtraction sign with this denominator. So this is what we call multiplying by the conjugate. So the conjugate, all that we're doing is if I see something like this where I have a plus or a minus sign with the radical in the denominator, the conjugate just means take whatever the sign is and switch it. So I'm going to multiply by, instead of 5 plus square root of 2, I'm going to multiply by 5 minus square root of 2. And again, that's going to happen on both the top and the bottom. Now the reason we do this, I'm going to start with the bottom here. The reason that we multiply by the conjugate, again, because this is a binomial times a binomial, we have to double distribute. Take the 5, distribute it through to both terms. Then we have to take the square root of 2 and distribute it through to both terms. But let's see what happens here. When I take 5, multiply by 5, I get 25. When I take 5 and multiply it by minus square root of 2, I get minus 5 square root of 2. When I take the square root of 2 and multiply it by positive 5, I get plus 5 square root of 2. And when I take square root of 2 times minus square root of 2, I get minus square root of 4, which really is just, which is just minus 2. But now if I look in this bottom here, if we look here, negative 5 square root of 2 plus 5 square root of 2, these two terms are going to cancel each other out. So in my denominator, I really just have 25 minus 2. So now if I see here, I've gotten rid of my radicals in the denominator, which is exactly what I needed to happen. Okay, I still have to do my numerator, which again I have to distribute the 3 through to both of these terms. So 3 times 5, that's going to give me 15. 3 times minus square root of 2 is minus 3 square root of 2. But now up here I can't really do anything with this, so this is just going to stay exactly as is, 15 minus 3 square root of 2. And the bottom here, I can simplify that bottom part, so that's going to become 25 minus 2 is 23. The top part is going to stay as 15 minus 3 square root of 2. And now this is going to be my final answer. Now, the only thing that I have to worry about here is what I like to call, and I don't know if anybody else uses this, but I like to call it the smiley face. I see a smiley face happening here. So if this is the issue, I have to look at these three numbers. And I have to say to myself, do these three terms have any sort of common factor? Well, in this case, 15, 3, and 23 do not have a common factor with them. If all three of these were to have a common factor, I would want to divide all three by the same factor. So let's just, for instance, say that this 23 was a 21. They would all have a 3 in common. So I would just divide all three of these numbers by 3 and then rewrite what the answer is. Okay, but in this case they don't have any common factors, so I don't have to do anything to them. Alright, let's try one more of those so that we are 100% sure that we understand what's going on. So let's say I had the fraction 3 over the square root of 7 minus the square root of 2. So obviously here we see that we have radicals in the denominator, and not only do we have radicals in the denominator, it's a binomial with radicals, meaning we see a plus or a minus here. So in order to rationalize this denominator, we are going to need to multiply by the conjugate, meaning take whatever's in the denominator and just change this middle sign. So instead of multiplying by just radical 7 or just radical 2, we're going to multiply by the radical 7 plus the radical 2. And we're going to do that on top and on bottom. So this time we'll do the top first. We'll take our 3 and we'll distribute it through to both terms. So up top we're going to have 3 times radical 7. That is 3 radical 7. Again, remember, we can't take a number that's outside of a radical and multiply it by something that is inside of a radical. Outside multiplies by outside, inside multiplies by inside. So this is 3 radical 7 plus 3 times radical 2 is going to be 3 radical 2. So now on bottom, again, we do the same thing. We're going to double distribute here. We're going to start with the square root of 7 times the square root of 7. So square root of 7 times square root of 7 would be square root of 49, which is just going to end up to be 7. Then I have square root of 7 times the square root of 2. So 7 times 2 is 14, so that's going to be plus the square root of 14. Then I'm going to do the minus square root of 2 times square root of 7. That's going to be minus square root of 14. And then minus square root of 2 times square root of 2. So again, square root of 2 times square root of 2 would be square root of 4, which is going to end up being 2, but it's a minus 2. So just like in the previous problem, again, we see here that a positive square root of 14 minus square root of 14, these are going to cancel each other out. And in the denominator, I'm going to just be left with 7 minus 2, which is going to end up being 5. In the numerator, none of this can be simplified, so we leave it as 3 radical 7 plus 3 radical 2. And then I look at my smiley face and I say, can I simplify any of those? Well, 3, 3, and 5 do not all have a common factor. So the answer to that question is no. So this right here is going to be my final answer.